Hey everyone. This is going to be a video on how to do logistic regression using SPSS. Gonna share my entire screen with all of you, assuming my system will let me do that. So, what I've got is a version of SPSS. I need to grab some different data. So do I want to proceed? Yes. Do I care about any of that? No. Save changes? No. And of course it goes away. So anyway, with logistic regression using SPSS, SPSS actually allows you to use a whole lot of different types of output data when you're trying to do that. You can use, there'll be times like the data that I give you where we're going to be looking at dichotomous outcomes, so basically 0 and 1. There'll be other times when we're looking at outcomes that could be, say, star ratings or something like that, and trying to predict is someone going to give you, say, a 1 star, 2 star, 3, 4, 5 star review, that type of thing. Despite what a lot of the data science textbooks that you might actually read, logistic regression actually does let you do that. When they say it doesn't or when they say it can't, they're just wrong. End of story. And if you follow along with enough actual statistics and stats classes, you'll realize that a lot of the material that is, in the way that it's covered on in data science textbooks is somewhere between wrong and totally wrong. So what I'm looking for now is trying to get a data set that I've used several times before. So I'm going to use this study data down here. I'm importing everything into SPSS. You can see all the different variables that I've got here, and I'm going to go ahead and click on OK. The data set that you're going to use is going to be different. So there's a whole lot of data in what I'm looking at, which is why it took so long to import everything. And for purposes of this video and for purposes of you actually doing logistic regressions for real or any type of data science, uh, what I've done here is I've got 6 different variables that are all starting with R and 44 different variables that all start with W. I made the model that's here so I know what variables belong and I know what variables do not belong. The variables that belong all start with R, and the R just stands for the right answer. The W is for wrong answer. So when we go to analyze these, if any data science or if any uh, logistic regression modeling actually does exactly what we want it to, which is to pull out the important variables while trying to obscure all the wrong variables from being selected and being shown as, say, statistically significant. All of our models should have this R1 to R6 as being important. So now that I've got this uploaded, we can actually see what's actually going to happen. So I'm going to click on Analyze. I'm going to come down to Regression. And in Regression down here is Binary Logistic. Because I've only got the 2 outcomes that I'm looking at, Binary Logistic is what we need. So I can go ahead and click on that. In the lab, and if you talk with actual statisticians, we're going to have a dependent variable, which is the common terminology for just about everyone. And then we're going to have a independent variables, but for whatever reason, SPSS calls them covariates. Why? I don't know. Ask them. They're the ones that do this stuff. I don't understand a lot of why SPSS does what it does. All I know is that it does what it does. Now, to get all the variables in all the, from a statistics textbook, would be called independent variables collected in here all at once, I can go ahead and highlight all of them and hit the button over here to put everything over here. Now, looking at some of the variables, everything's over here. And because we know that, and this is actually true in a lot of the data that you're going to be dealing with in the real world, you might have, in this case, 50 different variables to look through. However, you are only going to have what are called the vital few. One way that we can get to that vital few is to eliminate some of the variables that we don't need. Now, a method that we can do with SPSS is we can use where it says here, enter or method, and then enter. I'm going to click on here, and I'm going to click on backward conditional. What that does is it puts all the variables into the model, and then it actually deletes variables that are not statistically significant and removes them automatically. What that does is make your job as a statistician a lot easier, or as a data analyst a lot easier. If you talk with a statistician, they're going to tell you that a lot of these methods are not very good and give you a whole bunch of reasons why. And in all honesty, if I was going to do this as part of a job somewhere, I wouldn't be using these methods either. The method I'd be using is using the enter method, look at everything, then selectively remove variables a couple at a time, rerun the model, select a few more variables to remove, rerun the model, so on and so forth. I'm trying to make it easy on you, so let's just use backward conditional. As long as a backward conditional gives us a model and the assumptions behind the model are good enough, I'm totally fine with that. Now, if we look at some of the things that we have over here, so I've got this one thing that says categorical. Some of the variables that we have are actually categorical. In the case of what we're looking at here, R5 and R6 are dichotomous. You can think of these as, say, a data set where you're asking a question like, have you ever smoked? Yes or no. Have you ever used illicit drugs? Yes or no. Have you ever done this or that? Uh, if we're trying to find, if we're trying to find links between data and, say, health outcomes, we might have a lot of information that's like this. Because I've only got two categories, or a lot of these are dichotomous, putting them in the categorical covariate isn't going to help us out very much. However, if we had a column here of data where, say, we had 0, 1, 2, 3, 4, and 0 refers to, say, being a white person, 1 is African American, 2 is Latino, 3 is a Southeast Asian, 4 is, say, other or something like that. Then we would want to put that in here and uh, select some of the things that are down here. Again, we don't need to do that because the data I have and you're using is not set up that way. So I can actually click on cancel. Click on save. Some of these might actually be fairly useful. Uh, with logistic regression, what it does is it tries to predict whether or not someone, so basically whether or not one of the rows of data that we're looking at belongs to a certain group or a different group. So having the probabilities could be useful. Again, for what you're doing here in this class, you don't need to do this, but sometimes it is actually uh, valuable. And then there's this group membership thing here. This tells you, based on what's called a cutoff, uh, whether or not uh, it's predicted that one of these individuals belongs to the group of no or yes. The outcomes here are dichotomous, meaning that the outcomes are generally going to be, say, if we're looking at cancer, do you have cancer? 0 is no, 1 is going to be yes. So looking at how these group memberships actually stack up, that could be important. If I go to options, I'm going to click on continue here. I'm going to go to options. And down here we have what's called classification cutoff. We've also got goodness of fit test, which is usually a good idea. Confidence interval for what's going on there. That's also a pretty nice thing to have. The classic cutoff here is going to be 0.5. We can actually manipulate that to see if changing the cutoff actually affects, say, the accuracy that we're looking for or not. I'm going to keep it at 0.5 for now. So I'm just going to go and click on continue. Style. This is garbage that I still haven't found any use for yet, but whatever. So now that I've got the dependent variable that I want, and I've also got all the independent variables that I want, even though SPSS is calling them covariates, I don't know why. Again, go yell at the people at SPSS about that one. It probably has more to do with the fact that SPSS is a statistical package for social sciences. And a lot of psychologists and sociologists call their independent variables covariates, but whatever. So I'm now going to click on OK. And you can see the logistic regression is running and doing its thing. And we've got an outcome. So scrolling down, you can see that there were 30,000 data points in here. The original encoding and decoding is basically 0 and 1. Looking at this classification table, and you can see that it says up here, block 0, beginning block. It puts everything into the 0 category, meaning no. We need to improve upon that. So, and I don't know why it does all this stuff at the beginning. But now it can get to block 1 method equals backward stepwise. If you remember back to the multiple linear regression video, you had 2 different options. One was actually called backward, the other was called stepwise. Why is it backward stepwise here? Again, I don't know. Go yell at SPSS about that one. But you can see that it took a lot of iterations to come up with a model that it thinks is the best. A lot of the stuff don't really care too much about. Contingency table, blah, blah, blah. Keep on going through all of this stuff. And what we have here, or now anyway, is a classification table. Back in week 2, we were talking about conditional probability and medical diagnostic tests and stuff like that. And what is going on here is basically we've just created that test. We have in our data set some 0s and 1s, and these are, say, known to be 0 and 1. And then we have the predicted outcome, which means we're using the model that was just created to try to predict, does a particular row, so does a particular person seem to belong to, say, group 0, meaning no disease, or group 1, meaning they do have the disease. And as we scroll down, get down all the way to our last data point here in step 43, we can see that the model is really, really good at predicting and know correctly, but its own the error rate is 11.5, or it's only 11.5% correct in predicting that someone that has the disease actually has the disease. So the overall So you can see the overall percentages here. So the overall accuracy of this particular model is 91.5%. But again, just like we had back in week 2 with the medical data, you can see that it's not very good at predicting a 1 as a 1. And when we scroll through all this garbage, oh, I know, takes a while to get there. But once we get to it, you can see down here at step 43, it decided that R1, 2, 3, 4, and 5 are actually statistically significant and belong in the model. Now, if you look at the data that's behind me, there's an R6. Like I said, R1 through R6 are statistically significant. They are the only things that went into the model that I made. So what has just happened here is one of the variables that is actually in the model wasn't selected for the final model, and it's because it didn't look like it was statistically significant enough based upon the data that we have. So what I did here is I created an algorithm, or I created the model by saying when a certain value is above whatever, the top 5% are going to automatically be given a 1. And then to give it some variability, I created 5% random data. So what that's going to do is you have approximately 5% of the data is what we want, or is a 1 and a legitimate 1. 5% of the data is just a 1, but it's also random. And just to make the computer thing, just so we don't get too clean of results. And then when we look at some of the other variables that have also come up and look as though they are statistically significant, we notice that there's W13, W14, and W21. Now, as I stated, anything that's marked with a W is a wrong variable. Uh, but just because of how the software works, it's selecting 3 variables that I know are wrong and putting them in the model. And it's left out a variable that I know is right, which gets to a point of, allows us to talk about with any type of these models, there are going to be what are called spurious correlations. These spurious correlations can lead you to believe that some variable is statistically significant when in fact it's not. Looking at because I made this model, so I know what the right answer is. I know that the model picked up some things that shouldn't be there and left out a thing that should be. When you're doing this for real, you don't know what the correct answer is. So almost by default, you have to look at everything that you were given and then try to see, does it actually make sense or not? Sometimes you can look at things and look at the values that pop up and see whether or not it makes sense. Uh, Sometimes you can look at the values that pop up and maybe you're going to be learning something new. Just as an example of this data set that I worked with, we're trying to predict whether or not a vehicle is going to come back for warranty repair and a certain type of warranty repair. And according to the company that was sponsoring us, uh, the company literally came out and said, uh, the data manufacturer does not matter, so you don't need to put it in the model. It's got to be one of the other variables. And if you talk with some people that work in industry and you say something about, do you think data manufacturer has something to do with the quality of the product? They'll say, yeah, never buy a product made on a Monday or a Friday. Why not a Friday? Because no one's paying attention. They just want to get everything done so that they can go home and start their weekend. Don't buy anything on a Monday because everyone's going to be so tired from the weekend that they're not going to be concentrating on everything. So there is kind of like that joke in that background. But looking at all the other data, literally nothing seemed to be working. So I put the data manufacturer in there, and it turns out that was the key. A variable that the experts specifically said should not, would not, and isn't going to be something in the model ended up being the most important thing for determining whether or not these vehicles were coming back for repair or not. Um, some of the variables that popped up when you looked at them, the only thing that you could really tell is these don't have that big of an effect. And some of the stuff is just weird. Like if you torque a bolt a little bit too much, that's gonna increase your chances of being recalled. But if you don't torque it enough or you torque it way beyond that, it's going to be perfectly fine. So some of these responses were quadratic, and that was weird. But anyway, looking at what we have here, if we're going to assume that this is all data and we don't know what the underlying model is, we would actually look at all the variables that are here and think, okay, this is what's actually going on. And you can see down here, it says, tells you everything. So model if term removed. I have no idea what this whole list is supposed to be doing, but you can see some of these look like they are statistically significant. Some look like they're close. So it looks like W13 and W14 could be really close there. Again, that is one of these spurious correlations. Now, if I want to try to improve the matrix where we're trying to predict if someone that's a one is a one, someone that's a zero is a zero. Again, I can go down to regression, binary logistic. So everything is already set up again. This time I'm going to go to options, and I'm going to set this cutoff from 50% to say 40%. I'm also going to get rid of the goodness of fit test. And I'm going to click on continue. And let's see what actually works here. So I can click on OK. It's going to take a moment to go through all this stuff. And you can see it's working really, really hard down here. And then poof, there are some things. Again, 30,000 data points. Again, initially it's predicting everything is a zero because most of the data is a zero. And then we get down here to step 43. And when we come down here to step 43, we can see that now the model is 26.1% accurate at predicting someone with a one as a one, and it's 99.8% accurate at predicting someone that's a zero is a zero. So we actually did improve quite a bit, but there's still a lot of the people that, based on the data, have the disease, but are being predicted to be perfectly fine. So we can go back, we can work on that again. Maybe, uh, just maybe, we can actually come up with a cutoff point that gives us really, really great accuracy on the model, as well as really great accuracy in predicting a zero is a zero and a one is a one. Since we just saw that going from 0.5 to 0.4 seems to be have improved things. How about we change that to 0.3? Again, this isn't something that you need to do for the lab, but this is something that if you are going to be doing uh, statistical modeling, something that you will need to take into account. So I'm going to click on OK again. It's going to do its thing, and it's going to start getting faster, faster, faster. All right, there it is. So again, initially everything gets counted as a zero. Go through all this. Step 42, we found out, or we found what the best model seems to be. Coming down here again, And now if we look at what we've got here, uh, probability of predicting a zero is a zero is 98.9% accurate. The probability of predicting a one is a one is now about 49% accurate. So this is telling us that changing that cutoff point is actually having a fairly positive effect on whether or not our model can predict if someone has disease, that has the disease, actually has the disease. We can go back, we can try doing this over and over and over again if we really want to. However, again, this changing the cutoff value is more of an issue when you're dealing with the real data and you're trying to come up with a better model, something that does a better job of predicting, say, the disease in this particular case. If the whole point of this was to come up with, say, the best cutoff point with the best variables for the data set, we could keep going on with this for a little while. Since that's not what we're about here, I'm going to leave it at that. Now I can go back to analyze, and once on analyze, go to regression, come down to binary logistic. I'm going to change my data set. So this time I'm going to look at the same data set, but it's going to be 5% real, 25% fake data. I'm also going to go back to options. I'm going to change that back to 0.5. And now let's see what actually happens when we do something like that. So click on it, it's going to do some stuff. It's given us an outcome. And again, you can see that's predicting everything's a zero. And then as we step through all this, it only took 37 steps instead of 40 something like it did last time. If we look at the final matrix down here, we can see that the model is really, really good at predicting someone without the disease, doesn't have the disease, but it's absolutely horrible at predicting whether or not someone has the disease. So that's another issue that comes up. It's another reason why we need to look at these outcomes right here. Because looking at this, I might be able to look at the data that I've got here and say, once I get down to the statistically significant terms, which are coming sooner or later. So if you look at what's going on here, it's chosen that R1, 2, 3, and 4 are statistically significant, and they are. It's also decided that a whole bunch of these W variables are statistically significant. But again, because I made the data, I know it's not true, but the data, it does seem to be fooling our software here. And again, this is a thing that is going to happen. And then we also know that there's R5 and R6, which are part of the model, which logistic regression didn't actually find. So what does that actually tell us? Well, with the data that we have here, uh, because the signal to noise ratio is 5% true, 25% false data, we're going to see a lot of stuff pop up that shouldn't be in the model. And we're running the risk, like we are here, that one of our models is not going to have the right data or the right terms in the model, which is what's happening here. If we didn't know any better, we would actually have to go basically with what we've got here. We'd have to do some other model diagnostics, which one of them is the matrix that we were just looking at. If we're in a data science class, that matrix is called a confusion matrix. Don't remember what they call it here. But again, the big idea here is I can use the computer I can use the automatic system to determine what variables belong in my model, so I don't need to spend hours actually going through all this stuff. So again, I'm gonna see, what do they call it here? Um, that's not the right one. That's not it. So here they're calling it a classification table. Uh, these are also called confusion matrix. And I'm looking at the old stuff here, but whatever, you get the idea. Now, if I want to analyze, say, another data set, regression, uh, binary logistic, I'm going to choose one where, say, I've got a really high signal to noise. So 25% of the ones in here are correct, 5% of the ones are incorrect. So I'm going to drag these over, go ahead and click on OK and see what happens. And you can see that it's a thinking, running through everything. There we go. So again, you can see that it's classifying literally everything as a zero because that's the major thing. But once we make it through, so this time it took 40 steps to figure out what the best model was. We look at the classification table, get down here to the end, and you can see that the model that we have is 98% accurate in predicting a zero is a zero, and 83% accurate at predicting a one is a one. So this is a lot better than we've actually seen elsewhere. If we had data like this, could we go in and manipulate the cut value to hopefully do a much better job here? That is possible. Again, that's something that is beyond what we're supposed to be doing, but it is something that we need to worry about. So with this model, it is 94% accurate overall. And looking at the numbers we have here, I actually do feel pretty good about them. And when we come down, see if I can speed this up at all. So if we come down to the last step here, again, we're left with all of these statistically significant terms. And you can see that R1, 2, 3, 4, 5, and 6 were all selected as being statistically significant. But even with data where most of it is true values and actual ones, and we've just got some random variables in there that are flipping things around. We've got all these W's here, which are still being selected as being statistically significant. So again, we're still getting these spurious correlations. Now, if you think about the way that I created this data, by putting in random ones in the output column, what that's going to do is from time to time, you'll be analyzing data and you might be able to go in and find a whole bunch of variables that are statistically significant and are important for, say, predicting that outcome. But you might also have some people where the information you have, you know that, say, they have cancer, but the reasons they have cancer haven't been captured in the data that you have. So there could be, say, all this information could be data generated by various types of medical tests. But if you didn't do, say, genetics test, can certain types of genetics lead to more greater potential of having cancer? Most definitely. Just as an example for breast cancer, there are the BRCA1 and BRCA2 genes or something like that. If you have a certain version of BRCA1 and BRCA2, you are more likely to have cancer, breast cancer. So given the data that I've got here, if we didn't do the genetics testing, or if we didn't look for, does the patient have uh, that, they might actually have cancer, just not for a reason that we have data on, which is where that 5% data to kind of randomize things actually comes into play. So again, looking at the results that we have, there's a lot of stuff that just came up. All these W's, we know that they're wrong, but they're still in the model and they still look like they might be important. And if this was, say, a data set that I'm working at with at, say, a hospital or something like that, all these W's here might be variables that are suspected of being statistic or important, but we just don't know, and we're looking for proof that they are. These might be variables that we know for certain are not associated with it. And then when they pop up like this, we know that, okay, the model we have is good, but it's choosing some things that we know just can't happen. There's also, again, the other possibility here is that all these W's that just popped up, they are, they could actually be things that we need to investigate further in later research projects. So even though the W's, if again, if this was a real data set, all those W's, those could be things that you need to investigate later on, try to get a better idea of why they popped up and what you can actually do about it. Uh, but we know that at least this time we got all the R variable or all the correct variables were selected. So we can go in, we can use this model and hopefully do, if again, if this was a real data set, hopefully do some real good for the people that we're going to be serving or who are going to be part of future predictive outcomes modeling and stuff like that. So again, if I'm going to try to analyze a data set, I have to go to Analyze, come down to Regression, come over to Binary Logistic. The dependent variable, or the variable that I'm interested in trying to predict the outcome of, goes up here. All the other variables that I want to test go over here. And when you look at all of these variables, and so like I've highlighted them there, you notice that there's this white thing that pops up. I can actually click on that, and it's trying to create a term, what's called an interaction term. The interaction term that's right there is actually totally useless. Uh, but I could actually use that to try to come up with new variables if I needed to. Suppose for a moment that with some of the data that I've got here, like I can see R1, R2, R3, and R4 are all continuous variables. 3 and 4 are continuous but discrete. R1 and R2 are continuous. Something that I could actually look at and do here is I could try to create new variables, say for R1, and then create, say, R1 squared, R2 from here, and then say R2 squared, and R3 squared, and R4 squared, and W1 squared, W2 squared, W3 squared, and all the rest of these. Again, that is beyond what we need to be doing here. For you guys, all you need to do is be able to go to Analyze, Regression, Binary Logistic, select the variable that you want to try to predict. All the rest of the variables that you have go in this block, which for whatever reason, SPSS calls your covariates. And the categorical stuff, again, for future use, you might need to use that. Save the probabilities. We don't need that, but I'm not calculating. So you know what? I don't care. Let's see what's going on. The options, confidence interval here, cutoff down here, and those help out quite a bit. And then you just click on OK, and everything should hopefully go your way. If you have any questions, feel free to send me an email, and I can run you through this stuff. I know some of it is a bit confusing and some of it is a bit, or can be a bit, off, or it, it, uh, what I want to say here can be a bit, nerve-wracking if you don't know what you're doing. You could get, pretty, pissed off at the system, and I totally know why. But, it is what it is. And what we've just done here is the basics that we need, for future data analyses and a bunch of other things. So with that, I'm going to stop this recording and look forward to torturing you all later. Have a good evening.